You want to talk about the unit circle? Let me move my camera. I'm going to move my camera over here. Boom. All right. Finally get to do what we love. Yeah. So, as you can see, I got the thick x-axis, the thick y-axis, and then the thick circle with the center at 0, 0, the origin, and radius 1. All right, that's really important. This is called the unit circle because the radius is 1. The equation of the unit circle is x squared plus y squared equals 1. So I have that written there. X squared plus y squared equals 1. The center is at 0, 0. The origin, the radius of this circle is 1. That's really important because that's going to help us determine some coordinates on this unit circle. This coordinate right here is 1 unit away from the origin, 1 unit to the right. So this would have a coordinate 1, 0. All right, we moved 1 to the right, 0 up or down. Nothing, we didn't move any vertically. All right, this coordinate here would be 0, 1, because in order to get from the origin to this coordinate here, we would not move any left or right. We would move up 1 unit. So 0, 1. All right, and then over here to the left, this coordinate here would be -1, 0. And then this coordinate here would be 0, -1. All right, very, very important there. All right, and then you see these thin lines going through the origin as well, right? You see these thin lines. These thin lines intersect this circle and these red marks that I'm making. All right. So the distance from the origin to each of those coordinates is 1. Distance is 1, right? But those coordinates are going to look a little different than the coordinates that we have already put onto our unit circle. All right. So the distance is 1. If you remember the distance formula, you can prove that the distance is 1 once we have those coordinates. But the idea first is to get those coordinates. We don't know what they are. All right. So the first thing I like to show whenever I teach the unit circle is the degree measurements along all of these angles, right? These I can look at as angles. So I'm going to draw up here in blue. If I consider this to be an initial side and this to be my terminal side of an angle, then you can see that this right here, I can label that angle, all right? I could say, okay, well, here's the initial side. Here's the terminal side. So what angle would that create from here to here? And so on. So then I could say, okay, this initial side here and this terminal side. What angle is created? What degree measurement is that, right? So the unit circle is very special in that the angles never change and the exact values, what we're going to call exact values, never change. So we learned in the previous video, this right here represents 0 degrees. We have a 90-degree angle here, 180-degree angle here, 270 degrees here, and then of course 0 is also 360 degrees, a full rotation. What are those other angles? Well, this first angle would be 30 degrees. This angle here would be a 45-degree angle. This angle here would be a 60-degree angle. All right, there's a little pattern going on. So basically, I'm taking the first quadrant. The 45-degree angle is cutting the quadrant in half. The two 30 and 60 degree angles are cutting that quadrant in third, right? 0, 30, 60, 90. That cuts it in third, in thirds, and then 0, 45, 90 cuts it in half. All right, so keep that in mind. But I like to look at it as a little pattern. 0, 30, 45, 60, 90. So the pattern is from the quadrantal angle to the next, I'm going to add 30, 15, 15, 30. So I'm going to do the same thing over here in quadrant 2. I'm going to add 30 to 90, get 120. Add 15, get 135. Add another 15, get 150. And then, just to make sure, add 30 and you get 180. All right, so it's a little pattern. Okay, do the same thing for quadrant 3. Add 30, 15, 15, and then 30. We'll be at 270. And then finally, quadrant 4, add 30. So see if I could squeeze it in here. 300, 315, 330. All right. That's very important right there. Those angles are very important. Now, we learned how to convert angles in the previous video from degrees to radians. So we definitely want to know what the radian measurements of these angles are. You can memorize them, or you can convert each of these degree measurements. For the sake of space, let's just get the radian measurements written down for the first quadrant. And I'll do that in orange. Okay, so of course this is 0 radians. I'm not going to write rads. We're just going to understand that the orange, it actually looks a little yellow. Let's get this darker orange. So that's 0 radians. Okay, we know 180 from the previous video. We know 180 is pi radians. So I can actually label that one pi radians. So if 180 is pi radians, that means 90 is half pi, or pi over 2. If you were to convert all these other angles, what you'll see is the 30 degree angle would convert to pi over 6. The 45 degree angle would convert to pi over 4. And then the 60 degree angle would convert to pi over 3. It's kind of hard to see. Well, you can see it pretty good. All right. And then you can convert the 120, 135, 150 degree angle in quadrant 2. And then the angles in quadrants 3 and 4. Convert those to radian measurements. And you can fill out this whole circle in terms of the degrees, the radians, and then those coordinates that we have. But we still need those other red coordinates that I've plotted. All right. And so there's a pattern that I like to teach to memorize where those coordinates are, or what they are, because it's very easy to get a little mixed up here. So this middle one is always going to be some variation of square root of 2 over 2, square root of 2 over 2. And when I say the middle one, what I mean is that 45 degree angle in the first quadrant is going to be root 2 over 2, root 2 over 2 in terms of x and y coordinates. So that represents the x and y coordinates of that point. This 135 degree angle is going to have the same exact root 2 over 2 coordinates, except will be in quadrant 2, and therefore the x will be negative. So we can plot that one, or we can write that one like so. Okay. So also you can think about symmetry. Those two coordinates would be symmetrical over the y-axis, and therefore you can use symmetry to get those, what we're going to call exact values. Now these other two are very easily mixed up. This coordinate here is going to be root 3 over 2 and 1/2. And then this coordinate is going to be 1/2 root 3 over 2. All right, and then, like I said, you can use symmetry and find the other coordinates for the other quadrants. So in other words, since 60 degrees is 1/2 root 3 over 2, 120 degrees, which is in terms of coordinates, that's the reflection across the y-axis. So I could say, okay, well, this coordinate is going to be negative 1/2 root 3 over 2. This 150 degree coordinate is going to be negative root 3 over 2 positive 1/2, and so on. And you can continue to fill out quadrants 3 and 4 very similarly. So with that in mind, let's just look at the first quadrant. All right, so what is the unit circle used for? Well, since I've only cut out the first quadrant, we're only going to discuss the first quadrant, and then we can talk about more in a future video. But let's see if I can do right there. I'm going to write some relationships down. I'm going to say sine. Let me thicken that up a little bit. Sine. We'll just say, we'll say sine theta is equal to y. Cosine theta is equal to x. Tangent theta, which is sine over cosine, is equal to sine is y and cosine is x. What in the world does that mean? Well, if we were to ask to find the exact value of, let's do something very easy for now. Let's do sine of 90 degrees. All right, sine of 90 degrees. Well, if you know your unit circle and you have an angle such as 90 degrees that lies on the unit circle, then you can easily calculate this. Sine of 90 degrees. So find 90 degrees on the unit circle, which we have here. All right. We know that sine is the y-coordinate at that particular angle. So sine of 90 degrees, look at the coordinate here. Sine is the y-coordinate. So sine of 90 degrees is equal to 1. If you were to type sine 90 degrees into a TI calculator, making sure you're in degree mode, type sine 90 degrees and hit enter, you'll get 1. And that's why. All right. So another example would be, let's say cosine of 60 degrees. So cosine of 60 degrees, you find 60 degrees on the unit circle, and then you look at your x coordinate at that angle, and that's your answer. So 60 degrees is here. The x value at 60 degrees is 1/2. That's the answer. Let me do this. Let me erase that circle there. All right, and that's it. Now, these can get a little tricky. So let's make this a little smaller. And then let's cut this out, do a couple more examples. So let's say I wanted to find, so number 3, oops. Let's say I wanted to find cosine of pi over 6. Now I'm in radians, which is the same idea. You still want to look at pi over 6. Where's pi over 6 on the unit circle? It's here. Find that angle on the unit circle. Identify the x value at that angle. The x value at that angle is root 3 over 2. So we're going to say cosine of pi over 6 is root 3 over 2. If you were to type cosine of pi over 6 into your calculator, this time changing your mode to radian mode, you'll get the decimal approximation for root 3 over 2. So you could use your calculator to check yourself by typing in cosine pi over 6, hitting enter, seeing what that decimal is, and then typing in root 3 divided by 2, hit enter, see if those decimals match. All right, number 4. Let's say I wanted to find tangent of pi over 4. Tangent of pi over 4 is the y value. So here's pi over 4. Tangent is the y value divided by the x value. So tangent is root 2 over 2 divided by root 2 over 2. I'm going to write it like this. Just to remind you of some basic algebra right here when you're dividing fractions. We know anything divided by itself is going to be 1. So this is going to reduce down to 1. But reducing these is not always going to be so nice and neat. So I definitely want to talk about dividing fractions. So whenever you divide fractions, which this is dividing fractions, root 2 over 2 is a fraction, divided by root 2 over 2. Whenever you're dividing fractions, you can change this to a multiplication problem by multiplying by the reciprocal of the second one. So copy the first one, root 2 over 2, change the division to multiplication, and then flip or use the reciprocal of the second fraction. And then you'll notice things reduce. Root 2 at the top, root 2 at the bottom, 2 at the top, 2 at the bottom. Everything reduces down to 1. And so tangent pi over 4 is equal to 1. All right. So let's do one more that looks a little weird. Let me take these off the screen. Let's say I wanted to find tangent of, let's say, 30 degrees. Tangent of 30 degrees. Same process. Find 30 degrees on your unit circle, which is here. Tangent is going to be the y value over the x value. So the y is 1/2. The x is root 3 over 2. So it's y divided by x. So it's 1/2 divided by root 3 over 2. Again, when you're dividing fractions, you want to copy, change, flip. That's the saying that I like to use. Copy the first one, change the multiplication, change the second fraction, flip it, change it to its reciprocal. So I have 1/2 times 2 over root 3. Now this time the 2's reduce, but I still have that root 3. And notice that root 3 is in my denominator. So I have 1 over root 3. All right. When you get into calculus, you will see answers expressed with radicals in their denominators. But in pre-cal, in Trig, in a pre-cal class, you may be asked to rationalize this. What that means is you don't want your answer to have a radical in the denominator. So to rationalize this, what you want to do is multiply by a ratio of 1. So kind of like conversion factors, you want to multiply by something that reduces down to 1. You want to multiply that number by 1. But I'm not going to put times 1. I'm going to put root 3 over root 3. What I've written down in orange reduces down to 1. But I chose to multiply the top and the bottom by root 3 because when I multiply the bottom by root 3, I get root 9, right? Root 3 times root 3 is root 9, which reduces down to just 3. And then the top, 1 times root 3 is root 3. That's it. So there is a lot more to it. Of course, we didn't finish filling out the unit circle, so we could definitely take some time to fill out the rest of this unit circle, the radian measurements to all these angles, as well as the exact values of the coordinates, and then get to the point where we can find, say, cosine of 210 degrees, figure out what that is, and so on. So the next video I may do some more unit circle stuff, but this video right here gives you a brief idea of how to use the unit circle, which was the goal. So I hope that was fun. If it wasn't, make it fun. I wonder, matter of fact, before I end the video, let's actually look at a filled-in unit circle. So there's the completed unit circle right there. Again, like I said, you can now use the idea behind what we just did with finding exact values, and you can find exact values of any angle that's on the unit circle. So let's say sine of 4 pi over 3. Sine of 4 pi over 3. Find 4 pi over 3, which is here. Sine is always the y value, which is root 3 negative root 3 over. If you were to find, say, cosine of 5 pi over 6, you would find 5 pi over 6 on the unit circle, which is here. You would identify your x value at that angle, which is negative root 3 over 2. So think about it. Why do both of them equal negative root 3 over 2? Now we can go in further depth about this unit circle, why those exact values are what they are, and I'll give you an idea. Maybe you remember 30, 60, 90 special right triangles and 45, 45, 90 degree special right triangles. So basically it's this circle is split up into all these special right triangles. All right, but there's that. Now it's back. Travis, what's up? You needed me a few months ago? You did take Trig recently. That was fun right there. Well, that is going to do it for the stream. Look for the math videos soon on the YouTube channel. Thank you guys for viewing. Check your name later.